Now for some perpendicular vectors. We're going to be doing some applications in the next couple of days where we're going to need to determine this, and here's how we do it. We are going to know if two vectors are perpendicular by analyzing their inner product. When that value for the inner product equals 0, that tells us two vectors are perpendicular, and here's how you solve for it. Say we are given vector A as x1, y1, z1, and B x2, y2, z2. You know, I really should throw this z right here, z1 and z2. Okay, those two, if you're in three-dimensional space, then you consider it. If not, you're just doing the application with the y values. I'll show you what I mean now. So let's figure out the dot product between A and B. Here's how we do it. You take your x's and you multiply them. And you add to that the product of your y values. If you are in three-dimensional space, you then apply the same concept to your z values. You take the product of them and you add them up. Let's do an example. Before I forget, I have this over here. The inner product also goes by another name. It's called the dot product. They're synonymous. So either way, inner product, dot product, it's what I'm about to show you right now. Here, now this is only 2 dimensions, okay? We don't have a z value, so that z value right here would just be 0, 0, which would be like adding a 0 right there, and it's not necessary. Let's pretend that those two vectors start at the origin right there. Okay, and this is our y-axis and our x-axis. And let's see what the values are here. Well, this vector, A, I guess we'll do A first. It's going negative 12 on the x, and it's going positive 16 on the y. And vector B looks like it's doing positive 12 on the x and positive 9 on the y. All right, well, if those are our two vectors, here is the dot product. I take my two x values, negative 12 times times positive 12. I add to that the product of my y's. My y value is 16 times 9. This comes out to be negative 144, and this is a positive 144. You add them up and you're going to get 0. If that happens, you get a 0, that means these two vectors are perpendicular, just like in our diagram here. And again, if you have a z component, you would just do it right here. You would include the product of the z's and add that up as well. Let's do an example in 3D. Say we are given vector A with coordinates 5, 2, 7. And vector B with coordinates 3, negative 4, negative 1. And we're asked to show whether or not these two vectors are perpendicular. Let's take the inner product. It just dawned on me, I just showed you the inner product, and I'm going to rewrite it. Well, here, I'm going to rewrite it here. We have the inner product of vector A and B. I put them in parentheses on the last slide. I didn't mean to, because this is not another vector. This is just a numeric value right there. We're looking to see if it's 0 or some other number. So what you're really doing is you're just taking the product of your x's plus the product of your y's, and if you have a z, in this case we do, it's the product of your z's. And you should not have parentheses like I did on the earlier example. We're just trying to figure out what's the sum of that. Here we go. We have 5 times 3 plus 2 times negative 4 plus 7 times negative 1. We get 15 minus 8 minus 7. You add them up and you're going to get 0. Therefore, based on the inner product, also known as the dot product, vector A and vector B are perpendicular. Okay, so we use the inner product or the dot product to determine if two vectors are perpendicular. But there are going to be times where we are going to need to know what is a perpendicular vector to some given vectors. I couldn't really decide which picture was better, so I'll just throw them both up here, and you look at, they're both basically telling you the same thing. It doesn't really matter what the angle between these, I mean, they could be perpendicular here, but they don't have to be. But what we're finding with the cross product of two vectors is a vector that is perpendicular with the two given ones. So let me just see if I can draw this in here. This may or may not be a 90-degree angle, but this cross product vector right here is perpendicular to B, and it would also be let me change that color. It would also be perpendicular to vector A over here as well, just like that. Okay? And that's what we're about to find here. Here's how you do it. Say we are given two vectors, and I guess I'm sick of A and B. Why don't we use, how about P and Q? Let's get crazy. We have vector P and vector Q. And I'm not going to get that crazy. I'm still going to call it x1, y1, z1. And x2, y2, z2. Okay. And here's how you find it. Now, I know I kind of said we're not going to revisit a lot of the stuff from the beginning of the year, but we do need to remember how to find the determinant of a 3x3 matrix. Here's how you set up the cross product. And now, unlike the inner product, this cross product is going to give us another vector. It's not a numeric value. We're going to use that we're going to solve a determinant using cofactors. Let's set it up like this. And how about red? You're going to take the unit vectors for each axis. Oh, sorry, that's an I, J, K. Okay, unit vector, unit vector, unit vector. And then you're going to take your first vector and write that down, whatever x1, y1, z1 is. And then you take your second one, whatever that is, you plug it in here, x2, y2, and z2. That right there gives you a 3x3 determinant, or a 3x3 matrix, and we're going to find the determinant of that. And I guess it would be nice to tell you what the notation for the cross product is. This picture right here has the notation, okay? Right here, that represents the cross product. All right, let's figure out the cross product between these two vectors. Say we're given P, vector P is 3, 0, 2. And vector Q is -1, 4, 3. Let's find which vector is perpendicular to both of these. We set it up as I, J, K. I'm going to put my first vector, which is 3, 0, 2. My second one, which is -1, 4, 3. That creates a 3x3 determinant. Notice how you can't just plug this into your calculator. We got ourselves some variables. Here's how we solve it by hand. You take that first row. The first row is an I, J, K. If you remember, you then cross out the row and the column with the i's, and you're left with this little 2x2. That goes here. 0, 2, 4, 3. You repeat the process with the j's. If you cross out the row and the column with the j, you're going to be left with a 3 and a -1, and then a 2 and a 3. And with the k's, if you scribble out the row with the k and the column with the k, you're left with these 4, which would be 3, -1, 0, 4. Don't forget to switch the signs here. Whatever this is, it's positive whatever that is, negative whatever that is, and positive whatever that is. Let's solve for this. We're now left with I times, how do you find the determinant of a 2x2? You take the product of that, which is 0 times 3, minus the other product, which is 4 times 2. I have a -j times, let's repeat the process, 3 times 3 is 9, and then I subtract the product of this. Now I'm subtracting a negative 2, so subtracting a negative 2 is the same as adding. I have plus k times, this product is 12, minus, well, even though it's minus a minus 0, so we're just subtracting a 0. Whether you're adding or subtracting a 0, it's not going to change. That leaves us with negative 8 times I, that's 11, so I have a negative 11 times j, and that, right, don't forget that's a 0, so that's 12 times k, plus 12k. That right there is the sum of unit vectors. If the question asked you to take that and write it as an ordered triple, that is not an ordered triple, that is the sum of unit vectors. The ordered triple was just simply negative 8, comma, negative 11, comma, 12. Not too bad. This word, you're not really you don't need to know it in high school, but I'll tell you right, I just love the word, and you're going to see it in college. If you take any math course dealing with the concept of perpendicular, you're going to hear the word orthogonal. That's how you say it, orthogonal, orthogonal. Well, that's all it really means. It's exactly what we're talking about. It's when two lines intersect or lie at right angles. Okay, they have perpendicular slopes to each other. That's what we're talking about. Perpendicular vectors, so orthogonal. Now, if we just look at the unit vectors we have here, everything's orthogonal. This right here, well, these two meet at a 90-degree angle. And let's see, these two meet at a 90-degree angle. And yes, these two meet at a 90-degree angle. Everything's orthogonal with each other. While we're at it, think about this. It looks like vector j right here is perpendicular to vector k and vector I. I guess vector j is the cross product for vector I and k. Similarly, vector I is the cross product for the other two, and vector k is the cross product for the other two. Everything's perpendicular with each other. Everything's orthogonal. Now for a little recap. When we are finding the inner product, which is also known as the dot product, if that has a value of 0, that tells us that the two vectors in question are perpendicular with one another. The other thing we talked about was the cross product. If I have found the cross product between two vectors, okay, cross product, that cross product is not only, now that's another vector. This right here is a numeric value. This is another vector. That vector that we find is not only perpendicular to one of them, but it's perpendicular to both of them. Please review the difference. People do confuse these two. Pause, rewind. You have that luxury. We're going to take these topics, these concepts we learned today, and review them in class tomorrow. Let's see. What do we got going here? Perpendicular vectors. Right there, day 5. No need to ask me what we're working on. Copy that in your notes right now, and you will know to open up to page 433. See you then.